So let's start. The good news is that this week will be easier because most of the subjects of this week are, I'll talk about it, are more about discrimination and models, and I'll give you some introduction about it. And I need someone to help me with the clock. And after 45 minutes, we'll cover some exercises from past exams regarding the subject that was studied so far. I want to speak about the following week, okay? So let's say that we can stay here until 3:30 today. We'll have a reinforcement of 1.5 hours. So I think this is okay. And another thing about the project, so the hardest subject this week will be GLM. Okay. And I'll try to speak a bit about it, but since the second project is for submission by this Sunday, so this Sunday, within 1 week, right? Is the third, it's not this Sunday? Monday, sorry. Don't worry, but there are, so there are two possibilities. So the first one is to tell you, okay, by Monday, try to submit at least 2 out of 3 questions. And the last question, submit it during the week, okay? And you won't be reduced by any points. So this is one possibility. And if you do so, we will have the option to start and give you before the exam, which will be by the 10th of June, the quiz, I mean. So before, you will have also 1 week to get prepared. And of course, the projects are the best way to get prepared towards the exam. But you will have 1 week, for example, only to solve questions from past exams and so on. And we will have time to give you an answer and a grade about your project. So I think this is the best thing to do. But if we will see that we won't make it, so there is some chance that we will change the submission day, for example, to the 7th of June or something like this. This is the second possibility. Okay. And then we will just publish the kind of basic solution. Okay, for the project. So these are the two options. On Sunday, 2nd of June, Sophie will help me with a poll. If it is possible to, for how many people can submit 2 out of 3 questions at least. If no, you choose. You will choose what to do. Okay. So this is by the 2nd of June. And if we will see that, for example, most of the course can manage it, so we'll go on this this possibility. And if it is impossible, we'll take the other way, which is less. I think it's you study less, but it's an option. Okay. So today, yes. Let me see. I'm checking it. So Isar sent me. So the quiz will be, yes, instead of the lecture, Monday morning, June the 10th, and then at Wednesday you won't have a lesson because there is this Shavuot vacation. So within 2 weeks you have this exam, and then you have a week off, And you can choose if you want to meet me during that week. For example, if we want at Sunday to have another preparation for the quiz or something like that. Okay. But this week we won't have, for example, a recitation. So, okay. So this is it. I don't know. This is a question for Izar. So I am responsible for everything which is connected to the projects. I write them. I give the grading tables and the instructions and so on, and the deadlines, and the exams are Izarlen. Okay. The quizzes. Great. Okay. So let's speak about mathematical subjects and less logistics. So I want to start with explanation about the question that you have in your that you had in your quiz. So I just had a screenshot of the quiz, so maybe it's less clear. So let's talk about what we see here. So we see this EEG. By the way, this is directly from your data. Okay, this was a clue for your first project about how you can check ergodicity and stationarity. Okay, and this is one possible solution. So whoever saw that had a hint, a nice hint. Okay, so this is the EEG2, and what we see here is that we have all the possible trials of this data, and this is the average. It's around 0, and now we want to see how did they check the stationarity. So they did the following. They look at the mean across the different trials, okay, for all of 1 minute. This is the number of trials, right? And this is 1 minute. I'm a bit confused. Yeah, it's 200 subjects, and then you check the mean. Yes, across all the time, right? Because you want to see for each subject what is the mean. Okay, so this is for subject 1, this is his mean, and for subject 2, this is his mean. Okay, excuse me. It's for half for all of the time. But like there's yeah, sorry, right, for 2 time means that the reason that they even take a copy. No, we don't okay. So the reason that this solution has 2 time beams, because you want to see that the average is the same across different possible beams. And then you see that it is, the average is okay, right? But now you're doing the same about STD. And when you are taking the STD at the beginning, you see that it is lower. And by the end, it's what no, at the beginning it's higher, and then it becomes lower. And already when you plot the data itself, you can see it here, right? Because you can see that it fluctuates around the same mean all the time. But the noise over here, the size of the fluctuations is much bigger for all the samples here than the other samples here, right? Therefore, you can conclude that it is not stationary. And if it is not stationary, then it could not be ergodic. Okay, so you don't really even have to look at the ergodicity. Yes. That something won't be stationary, but it will be ergodic. So I think that I said it. Yeah, I think that I said it. It's a matter of definitions. Okay, but we use the strong definition that if something is not stationary, therefore it is not ergodic. Yes. 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 Now, the idea behind the solution is that when you do it graphically, so you say, okay, here the STD is much smaller across time. So it doesn't matter what time bin I would choose because I see that this is not stationary already when I plot the data itself. Okay, so the main idea about this question was plot the data and then understand the answer. Yes. Yes.
Say if the two say it was stationary and we did
okay, so let's look at the ergodicity. Okay, so what is going here in the ergodicity? So in the ergodicity now we are just transitioning between the trials and the time. So here we are checking across different number of trials. Okay, we are checking the mean amplitude within time. So we see that the mean amplitude is also, is it stable here? I think yes, right? It's more or less stable. And the STD is the same. So you might say, okay, it looks like it is ergodic because all of the trials are acting the same way, right? But due to the definitions that we had during the recitation itself, since it is not stationary, it is not ergodic, okay? But even if you were mistaken at this one, I did not reduce points because I understand this is a matter of definition. Okay? Yes.
Is it the fact that it's like a slope, like it has a slope?
Yes.
But like if I just want that, could I also say it changes? Like it's just that I remember
so
looking at the slope and being like, oh, it changes over time.
Right. So this is just another way to show this one, right? Because it changes within time. Therefore, it is not stationary because across time it changes. Yes.
Yeah, so that's kind of, I almost confused about that. It feels to me like we're comparing kind of the same concept instead of looking at time average for one realization of the process versus ensemble. Like you're not, you know, this looks like we're still checking stationary means and we're not looking.
In this one.
Yeah.
Right.
Yeah, we're not comparing one realization and
So the idea over here is to look at, across different bins of subjects. Okay, so this is the difference. But again, it's a matter of definitions. Yet the idea itself is, could you conclude from one set of experiment to others? This is like the philosophical question that we are trying to evaluate mathematically. Yes.
So then, for it to be ergodic, like what would we would see just everything on the same line, right?
Yes. And I feel that EEG1 was like this, if I remember correctly.
yeah.
One, this is the one that is both stationary and ergodic, as far as I remember. Or the last one, I don't fully remember, but one of them was just, when you plot it like this, you have just straight lines, all of them look the same. Yes.
The idea that if one subsample to another subsample at different times, they are not the same. Like you want like the subsamples. Like if you take subsamples, then it should be like stable over time.
Across different subjects here.
Yeah, exactly.
Yeah. So if it would have been, as just Christian said, if it would have been a flat line, then it would have been also ergodic. But the problem here is not that it is different across different subjects. The problem is that it is not stationary. Therefore, it's not. Yes.
If there was not any graph from the stationary check,
Yes.
we would say that this is ergodic because they are changing in the same pattern.
So you might. So again, you might say that they act the same way. It is okay to say that, to say so, but then you would say it is not fully ergodic. Yes. But again, it's a matter of definitions, because some would say it is ergodic but not stationary. We stick to the mathematical strict definition. Okay, is it more clear now? Okay. And in the other question that I saw that some were mistaken. So we have this question, and we are talking about Poisson neuron, and we are asked to calculate the probability of 3 spikes within 40 milliseconds, given a sample rate of 100 hertz with a firing rate of R equals 10 spikes. Okay, so what we need to do is that we need to say, so how, if we have a sampling rate of 100 hertz, how many bins do we have within 4 milliseconds? 4, exactly. So we need to have 4/3, right? And then if we have a success, so it's the probability of a spike, right, within this bin. So what is the probability? It's 10/10 divided by 1,000, right? Why is it 10 divided by 1,000? Because this is 100 hertz, and this is the probability. And this is powered by 3, and then you need to do 1 minus the failures, right? Now I'm doing the failures. And this is powered by 1. And when you do this, you get the 0.0036. Okay, so the idea here was to use the same formula that was given in the recitation notes, but to do it on the binomial distribution. So this was the way to help you within the upcoming project that you need to compute a Poisson simulation. And in this simulation, you need to use the binomial distribution to create the simulation of the Poisson neuron. And you can go back to the recitation notes and you have like really kind of an how to write the algorithm. Okay, so please use it. Yes.
Okay, how did you get the delta from the sampling rate?
So the sampling rate, right? This is, so you have a sample, each bin is 10 milliseconds, right? So this is the delta t, and you need to divide it by 1,000 because you want to have it in, this is given in spikes per second. So you have to convert it to 1 minute, to 1 second.
You don't use the delta t for the milliseconds? Because,
No. Because I'm looking within each bin, right? So this is the probability within each bin. Is that more clear now? Okay. Okay, and now we need to complete the autocorrelation. So we had like really 3 slides from the last time that we were speaking, and these were more of the past examples. Yes. Yes, no problem. Divided by the sample rate. So why divide? So the idea here is that you say you want the probability of a spike within 1 bin. So what is the size of 1 bin? It's 10 milliseconds, but the probability is given by spikes per second. So this is why you write 10/1,000. So if you would just divide by 100, I don't know why it is working.
Because 10 by 100, 1,000 is actually 1/100, which is 1/.
Ah,
So why not just higher words by something? Does it keep the same? It's just that like this formula is easier to retain for me, and that's how.
yeah, I think it is okay. Yes. Yes, it should be the same. Yes, you're right. Yes.
Would you just use a Poisson formula instead?
So it won't give you the same. And for Poisson formula, the problem is that you don't know. Poisson formula is lambda E minus lambda T, right? So the lambda, excuse me? So lambda is R. One of them is, you don't know what to put here. This is the problem. You have one variable that you don't know what to put in it. Okay, so this is the reason why we don't use it. Okay, so lambda is RT or something like that, as far as I remember. I don't remember the exact formula, but again, it is written in the recitation notes. I think this is the T or something like that. One of the variables you don't have. 1 minute, I'll just open the air conditioning. Okay. Okay, more questions? Yes.
This is in project 2. It's not really about, make sure I understand correctly. It's not really about actually creating the binomial. It's about randomly extracting from your resolution. Right?
Yeah.
Randomly for each.
Yeah, but the idea is that you look at it like a success. If you randomly pick the specific value and it is lower than the firing rate, so this is like this idea.
Okay.
So it's just to understand the relation between the binomial and the Poisson. You're welcome. Okay, let's go into autocorrelation. And in this slide, I wanted by the end of the recitation, I wanted to speak about exam. I'll just wait a minute. It's okay. You can have a few more seconds. It's okay. Just finish. Are you sure?
Yes.
Okay. So we have here 4 examples of commonly known Poisson and so on neurons. And I wanted to look at this top example. So first of all, this is the example of a Poisson neuron. And would someone like to tell me what does a flat line in autocorrelation represents? Try to explain it in other words. So what does a flat line means in a function? Yes. Yes, I read.
That the I size of like the intervals between them.
Right, but in autocorrelation, I look not only on I size or first order I size, I look also at, yes. So what do you say? What does that represent? Any possible lag between 2 spikes is possible within the same probability, right? And the probability is given by the firing rate of 10. So we can also say that if we have a sampling rate of 1000 hertz, this is 0.01, sorry. Right? Okay. Now, what does that mean if we have a refractory period? Why do we have here a decrease in probability over here? Yes, why?
We adopted the fire to 0, so
Right.
multiply 0 by a number.
Exactly, because there could not be spikes within a certain period. For example, let's say that here it's for 10 milliseconds, right? And then you can say that within this duration, you couldn't have 2 spikes adjacent or any 2 spikes, so the probability is lower. And then it increased it is not just a step function. It increases because also in real neurons, it increases kind of linearly. And this is what you have in the simulation. You have a absolute refractory period, and you have this dynamic refractory period or something like that, that you have to do it linearly. And then why do we have these two horns over here?
Hypervalidity after a period will be higher. The neuron will fire.
Yes, because there is nothing that stops him to fire. So we have these horns, although there is no bursting, there is a higher probability that there will be another spike because nothing stops it now. Okay? And why not just go into a flat line like here? Why is it not just increase into a flat line? Because if you would just ask me, let's say more without thinking too much, I would guess that the refractory Poisson would look just like this, right? Flat lines, and then you have just this hole which reflects the refractory period. So why do we have these horns again? Why is there a higher probability? But the Poisson neuron is like this, right? So if you have a refractory period, you would just expect to have here a hole, right? And not these two horns, which are representing a bursting.
So you're saying at lag 0, it's so correlated with itself because your house is spike, so you see spike.
Ah, no, no, it is again, you still have these shifts. So the basic idea is that, let's say that you just turn it upside down. What is turning it upside down? It's like the saying, what is the probability of not having a spike within a specific time lag, right? And then when you turn it upside down, you say that it is a very high chance within the refractory period, and outside there is a lower, okay? So since the cut is clear, because you finished the refractory period, and now there is, again, the higher one. So this is the reason why it says that there is almost no probability of no time lag, of no spikes within this time lag, right? If you, again, I'm looking now at the upside down. So this is the idea behind it. And if you wish to understand it more, because I just don't want to go into too much details, but this is one of the papers from Izhar, that he said why autocorrelation is not enough to look at Poisson neurons, and that you have also to look at the hazard function, because the hazard function shows that it is a Poisson neuron. And this is something that you need to think within this project, because you're going to have a Poisson neuron, a regular one, and a one with refractory period, and then the one with bursting period. And then you will have to plot the autocorrelations and also the hazard function of them. And in the paper that you read, they don't look at all at the hazard function, and maybe by looking at the hazard function, you will have something new to say in response to the project. Is that clear? To the paper, sorry. Yes.
Just definition. So the first one is the Poisson.
Yes.
The second one is the Poisson.
No, this one is with refractory period.
Ah.
It's a Poisson neuron with a refractory period. Now this one is a burster. It's a Poisson neuron with a bursting period. So there is a higher chance of closer spikes within a specific period. And this is the bursting activity.
But from the definition, it's of a Poisson neuron, it says that it's independent of the training history. are trained. So like
Right.
neuron,
So you can say that this is an inhomogeneous Poisson neuron.
this is dependent on the history, right?
But
Yeah.
only for a short latency. But thank you very much about that. Now here what we see is the autocorrelation of an oscillator. And the idea in oscillator is that you kind of mix the refractory period and the burst-in, and they just come one after the other. And then you have these oscillations in the autocorrelation over here, okay? So this is the basic idea behind the oscillating Poisson neuron. Yes?
So what I don't understand is why the oscillator was also Poisson, because if we look at the burster and the one with the refractory period, after some time, they tend to converge to a flat line.
Yes.
Which makes sense because that's a Poisson neuron. But the last one, the oscillator, that is not converging to a flat line.
Okay, so let's say that you have 3 neurons, okay? And you have this one, and this one. Now, this one inhibits the neuron, and this one excites it. So, and they're also connected within each other, but it takes, let's say, 5 milliseconds. Now, this neuron fires a spike. So there is a higher probability of this one during this time to have a higher rate, right? Because it is excited. But when this one fires, it also excites this one. And this one inhibits. But this takes, for example, 5 milliseconds. And when it inhibits, then the rate goes lower. And then another spike comes to this neuron. And it excites and inhibits, excites and inhibits. And this is just about the basic mechanism of one of the ideas of the basal ganglia. This is one of the ways the basal ganglia is working. And in Parkinson's disease, we don't know why, but this rhythm is distracted. And the idea, do you know what is deep brain stimulation? Okay, so deep brain stimulation is that you put like you have this heart, how do you call it? The machine that you put in the heart, and you try to keep the same pacemaker, exactly. So you have the same thing in the basal ganglia for people with Parkinson, and they have this pacemaker that every time the oscillation is broken, then this pacemaker will fix it back just by electrolysing. How do you say? Stimulating electrically the electrifying, yes, stimulating electrically this region. Okay, so so this is a very nice thing to see, that we don't speak only at one neuron. Each neuron is connected to its own network, and you don't know how this network excites and inhibits it. Oh, and by the way, I saw one of the coolest things yesterday. There's something new in Science. I can send it to the WhatsApp group. There is a new paper about, they took a brain tissue and they did a microscopy, beautiful one of, that they have millions of neurons connected to each other or something like that. And you can really see the synapse connection, the synaptic connection within all of this huge number of neurons at a very, they call it mesoscale or even lower. It's amazing. I'll send it to you. This is also a beautiful image. Excuse me? I think they did a special microscopy that it's also involving machine learning in it. I don't remember fully, but this is really from 2 weeks ago, something like that. It's a beautiful paper. I'll send it to you. So I was just thinking about that you see that only now May 2024, only now there is some chance that we have the beginning of the possibility to start understand the neural circuitry and to start imaging it. So you understand that all of the things that we study now, it's like a way to detour the problem that we cannot image directly the brain. So we use this kind of methods to try to understand the circuitry by going around. Yes. Yeah. More questions? Yes.
I understand that yes, but I don't know why Poisson, because I would say that the oscillations look like very not stochastic. Determining the distance.
Yeah, because it depends on the rhythm of this neuron. Right. Is that more clear, my answer? In Poisson neuron is not fully random. This is just about the idea behind it, that you have some of organization. And here the organization of the neuron is this. It's this oscillations. And the idea in this course is that we try to find ways to do things that we can find the organization behind the randomness. Okay, so we don't have a lot of time now, right? Okay, let's have another 10 minutes. So I gave few examples from past exams. I really have to ask you, do you want to do something that, do you want to solve one like this? Okay, so let's solve one and then we'll go on to the next subject. So we have neurons in the dubolitis exactis nucleus of the mountain troll, which fire pairs of spikes within 5 milliseconds apart every 100 milliseconds. So I don't know how good you see it here, but you have pairs of spikes. So that the first one is always at 100, 200, and so on. The first question is calculate the Fanoff factor and the CV of the neurons, explain the results and the relation to a Poissonian neuron firing at the same rate. Okay, so let's try to do it. So let's start with so I'll just remind you that we have the Fanoff factor, which is the variance of spike count over the expectation of spike count. And we have the CV, which is the standard deviation of ISI over the expectation of ISI, right? Okay, so let's start with our ISIs. What possible ISIs do we have? 5 and 95, right? Because it's either 5 between the doublets or 95 between the second one in the pair and the next one in the next pair. Okay, so we have half for 5 milliseconds and half for 95 milliseconds. Okay, and now, so what is the expectation? How do we calculate the expectation? Why? I think 55, no? No, you're right, right. I can sum them and then split to half. This is here, the expectation is the average, okay? But if I want to use the formula, what I'm doing is the P of each ISI over the size of the ISI, and I sum all possible P and ISIs, okay? So here it's half over 5 plus half over 95. So this is 50 milliseconds, okay? And now for the variance, we need to use something a bit different. So, right, so I can also calculate the variance and then take a square root from it. So the variance is, you have again, the sum of the probability of a given ISI multiplied by the ISI minus the expectation squared, right? So let's use it in the formula. So the probability for the ISI of 5 is half multiplied by 5 minus 50 plus the probability of the second one, which is 95 minus 50. And this equals to 45 square, okay? Right, because each one of them is 45, and you have half of them, so this is 45 square. And yes, so I don't understand what did I do here. So the STD is 45, right? Okay, so the CV is the STD over the expectation, so it's 45 over 50, and this is almost around 0, right? It's almost 1, sorry. So why did I write that it's almost around 0? Okay, there is a mistake in the recitation notes. Okay, so this is almost 1. Now let's look at the Fanon factor. Okay, so now we need to do a spike count. And how do we do a spike count? We're doing the following. We have these 2 spikes, right? And now we need to decide of our window. So we will take what window that we want for the calculation. And okay, so the easiest one will be taking what size of window. If we will take 50, we have one window that we have spikes and another that we don't have. One window that we have and another that we don't have. So the easiest one will be to take the window that it is the same all the time. Therefore, the variance will be 0. Okay, so what window will be like this? Exactly. So 100 millisecond. Okay, so window of 100 millisecond will always have a var of 0 because it will be the same all the time, therefore no variance. And the Fanon factor will be 0. Okay? Now, if you don't have it, for example, in the exam, I don't want to say things for Izal, but if in the exam you don't see the 100 millisecond window and you choose something else and you have a different answer, it's okay because nobody told you what window to take. So I don't mean that you will be reduced if you didn't see it in advance, but look for the easiest way. Okay, the easiest way is always to look for either a variance which is minimal, which is 0. And if you have a irregularity in your data, there is one like this. Yes.
In this case, we can have to go to the expectation.
Right.
But in case we need it, it would be 4 for this window.
So the expectation is that you have 2 spikes within each 100 millisecond, right? So you have 2. Yeah, I think so. This is the expectation because you have again and again 2. So you have 2 spikes. So this is 0 over 2. Yes.
I'm sure, like you said, you video of stuff for like
Yes.
one is not in the video.
Yeah. Yeah. When you look at it, from a computer-like point of view, so this is all the index between 0 and 99. This is 100 bins. Okay. But yes. Okay. And now we need to draw the hazard and the autocorrelation. So I think the hazard function was clear from last time, but we'll just have something again like this. So if we said that this is our I size, right? So to calculate the hazard function, I think the easiest way to solve it is just by asking ourselves, where would we have values for the hazard function? Wow, it is so cold. I think this is from outside, but if I close it, it is impossible. Right. So what possible ISIs do we have in the data? So we have either in 5 and I'll do here the 5 and here the 95. Right. So what possible ISIs do we have? And this is the probability. So at 5, what is the probability for a spike?
Yeah, because
Half of the spikes are 5 milliseconds, right?
yeah, but if the human tires, so it must be away.
Either at 5 and I understand why you answered 1. It's okay. So if there was no spike so far, so the probability for 5, since this is the first one in line, is half, right? And if at 6, do I have any probability? No, 7 and so on. At 95, if there was no spike before, what is the probability of a spike? 1, exactly. So this is 1, okay? And this is the hazard function. Because the hazard is a question, what is the probability for a spike given that there was no spike? So you can solve it in one of 2 ways. The first one is just ask yourself, based on the rationality. If you didn't have a spike by 95, so you must have one now, right? Because you waited, and then there must be one now. And the other possibility is like we did in the recitation, that we were calculating the PDF and from the PDF the CDF, and then the survivor, which is 1 minus the CDF, and then the hazard function, which is PDF over 1 minus CDF. Okay, these are the 2 possibilities of how to calculate it. Yes.
I might have missed that, but my question is, for the hazard function, you really are not looking at anything other than what you need. Like you're not looking at the firing rate, right? Like you're really just looking at, okay, this happens. Like I know that this happens every 100 milliseconds.
Yes.
And then like if it didn't happen here, then it's half of it or a third of it or like a fourth of it, depending on the amount of spikes that you know.
Exactly.
There, right?
So you should look at it, yes, by looking at the ISIs. Think about it like you're waiting for your bus, and then it could either come within 5 minutes or the next one is within 95. So if we are living in a deterministic world and probably not in Israel transportation, so So there is a very high probability that if you miss the one here, which should have come within 5 minutes, the next one must come within 95 minutes. And I really hope that none of you will wait 95 minutes for a bus. Yes. Sorry. Yes, Christian.
So then, like in theory, all of the graphs will look the same. Like given you have the same amount of spikes in the time, and the only thing that changes is the x. Because like this is for 2 spikes, but if you had 3 spikes, then it would be 0.33 for the first like period, half and 1. But if you had 4 spikes, it would be like 0.25, 0.33, half and 1. Right?
I'm right, exactly.
So like they literally will look the same. They like base.
Yeah.
Only on the x.
Yeah, when it is given from a uniform distribution, you are right. But there is some possibility that you might have something like there is a doublet and then 1, and then another doublet and then 1, for example. And then this is different because you don't have the same probabilities. I think. Exactly. So you have here 5 in third of the cases and 95 in third of the cases and 1. No, so this is uniform. Okay, but the idea is that you might have something which is non-uniform and then you need to calculate it. And yeah, I read.
So if you have a hazard function that takes like 1/2 for 5 and 1 for 95, that means the survival for 5, 1, survival for 95 is 1/2, right?
Yes.
But I don't understand why. Like conceptually, why does 5 like
So if we take again the idea of the bus, so the survival is what is the chance that you missed the bus, right? So this is the idea behind it.
100% for 5?
For less than 5, yes. And then at 5 it drops to half, and then to 0. Yes. Yes. Hazard, yes, I think it. No, it might be also a flat line, for example, like in a Poisson neuron. Okay. Now let's look at the autocorrelation. So how do we? Yes, yeah. Yeah. So hazard. In the hazard, you don't have ISIs bigger than 95, right? But you are right about autocorrelation. So let's count all possible time lags of the autocorrelation function, okay? So we have, the first one is 5. How many like this do we have? Within 250. Oh, it's not here, the 250, but how many like this? Probability is in half of the cases, right? Let's just write exactly the probability of one week. In half of the cases, we have a time lag of 5. In how many of the cases we have a probability of 95? Oh, great. These are the 2 ISIs, so this must be the same, right? Now, what is the next time lag that we might have between 2 spikes? So you say 105, do you think there is one before? 100, great. How many do we have like this? What is the probability to see a spike within 100 milliseconds? 1. Because if you fired at 0, there will be one at 100. And if you fired at 5, there will be another one at 105. Okay, and the next one, Kanike? Kanike, right? Arna, sorry. Okay, so you are, okay, sorry for the confusion. Yes. 105, and how many do you have like this? Half, right? Because this might be the first one in the doublet and the last one in the second one, right? This is the relation between this one and this one. Or this one and this one, okay? Next one is, so if you're on the second spike and you fired at 5 and you wait 105 milliseconds, it would be 110, no spikes over there. So it's only between the first one in the pair and the second one in the second pair. So this is 105. Yes.
The fact that you're doing range of 0 to 250, does that impact anything? Because like the third option out of the 6 will not actually have a button.
I didn't understand what
So
you
like,
said.
if it's half, that means that out of the 6 spikes, 3 of them will.
I'm sorry. So I said something wrong at the beginning. You don't look only until 250. You look at all possible ranges until 250. This could be maximum 250. Okay? What is the next one? I think there is one before. 195. Okay? And what is the probability to have spikes within 195? Half. Half. If I'm at 0, I'll have 1. I won't have 1 at 195, right? If I'm here on the first pair, I'll just plot it like this. 0, 5, 100, 105, 200, 205. So the one from 195 is between the 5 and the 200, right? Now, if I'm standing on the 0, I'm waiting 195 milliseconds. There is no spike over here. So therefore, the probability is half.
So basically, we're looking at the probability.
Yes. What is the next one? How many cases like this we have for the probability? 1. Great. And is there another one? 205, and this is half. And another one? No. Okay. So now we have the autocorrelation. And since nobody wrote us how to draw it, so we can draw it as a probability. So we have at 5, 95, 100, 105, 195, 200, and 205. And then we have at 5 the probability of half. At 95, another one at half. 100 is 1, half, half, 1, half. Okay? Now let's say that we are asked to write it as a rate. How do we make the transition from probability? This is the possible time lapse. So from probability to rate. Yes. So this is to from count to probability, right? But if we want from probability to rate, by the size of the bin. So we need to multiply it by the sampling rate. So let's say we have a sampling rate of 100 hertz. Then the probability won't be half, it will be 500, okay? Now, also in the quiz, okay, I asked you about the rate. So another way to solve the question about the rate is saying the following. Within 1 millisecond, how many spikes do we have? 1 second, sorry, not 1 millisecond. So we have at 0 and 5, 100 and 105. So we have right, all those that are in the rounds of 100 and those that are after. So we have 20. So our firing rate is 20, right? 20 spikes per second. And this represents probability of 1. So if I have a probability of half, this is 1. So the rate should be, here it should be 20, and here 10, exactly. Okay, and you have a question in the quiz just about that. So what is the rate function at a specific time lag? So you need to calculate the firing rate along the second, okay? What is the firing rate? And then you have the probability, and you just multiply them, okay?
Why do you say 1 over
It's not 1/20. I meant to write it. I'll do it just using 2 colors. So here, this is the rate. So 1 will be 20 for a rate, and 0.5 will be 10 for it. Yes.
Here, would it be 9 spikes per second because the 1005 will be
1,000,
those seconds.
right?
The same
So
way that, like if you sample it every 100 milliseconds with 3 spikes rather than 4 spikes. Look at that change. But
okay, I think that you say you look until, if you have here at 0, so you need to look until 999, right? And then how many pairs do you have until 999? You have 10. 10 pairs of spikes, therefore 20 spikes.
if you take the 0, then you don't.
Yes. Yes, exactly. Yes.
There is a 50% chance that within like after 5 milliseconds that the neuron will fire, but won't fire in like 10 spikes per second. It will fire like 20 spikes per second, just 50% chance that it will do it. So not really a 10 spikes per second rate. I mean,
Okay,
it's
so
correct if you look at the population and then like half of the neurons will fire, but if you're looking at one neuron, then fire like in 20 spikes per second, not in 10.
right.
That's 50%.
So the idea that when we're saying 10 and 20 is that you ask yourself, if we have this neuron and you shift it, what kind of rate would it meet? Okay, each spike of this neuron, if I take this and shift it only by 5, so you have here this, and this, right? So you ask yourself what rate each spike meets. So this one meets the spike and this one not. So for each one, so for each pair, you have only one spike that he meets. Therefore, they meet 10 spikes per second. Do you understand what I said?
What you will shift it.
Because the autocorrelation, beside the fact of just counting the numbers of possible time lags, it also could be used as a shifting. And this is how we compute, this is how it is.
Yeah, that one
written.
again. Looking at actual firing rate, then if it fires, then it will fire like in 20 spikes per second.
Right, but you look at, again, at for each pair, how many spikes did it meet by shifting? Is that clear? In a way.
Yeah.
Okay. Yes. You know what? Leave out the sampling rate. I think this way is more clear. Okay, because I said that you can divide by the size of the bin of the sample and so on, but just leave it away because what you really have to do is just count the possible spike within 1 second and then multiply the probability within this size. This is more accurate. Okay? Yes. Yes. So the idea behind the rate question is that if you shift the neuron, I just explained it to Ori. So Ori or Ori, what do you prefer? Okay. So if you shift the spikes, what rate does the spikes meet? So you say there is only one overlap each time, right? Because I shifted it by 5 milliseconds. Therefore, the neuron meets another probability of 10 spikes per second. Okay? Yes. So here, this is not a Poisson neuron because the Fano factor is 0. The Fano factor should be 1 for every possible P in a Poisson neuron. Yes. In the autocorrelation, there is no need to draw the 0, which will always be 1, of course. Yes. You don't, when you have the 0 here, you don't need to plot it. You can, for example, plot only the positive part. And this is, of course, for autocorrelation, this is symmetric. We will have the same, and here we always define it as 0. For cross correlation, no. Okay, so let's just say a word about, oh, and by the way, if you ask me about, there is one missing example over here that I'll add to the presentation. If you want to ask me about one of the best exercises to study towards the exam, this is one of the best one, that you are given with a hazard function and then you need to draw the autocorrelation. Okay, so you have the hazard function and you see that this hazard function, you can look at it, it has few parts. There is the straight line, right? And there are these peaks over here. So what do they mean? The straight line means a Poisson neuron, right? But the peaks are for Bernstein. Do you understand that? And then you need to think, how do you take this to autocorrelation? And I can send you a simulation in Python for this question. And then you can try together and speak about it and to understand it better. And if you want to understand it fully, we can also talk about it in class together. Okay? So you have here the refractory period probably, and then you have a Bernstein in the hazard function. And then you have a straight line, which means a Poisson neuron, right? Like you have here a combination of few possible hazard function, and this is very good exercise towards the exam because this is also about hazard, also about autocorrelation, and so on. Sketch, because you will have a pen and a paper and you need to sketch. This is the possible time lag, 1000 milliseconds from each direction. So it should be symmetric and so on.
So the exam is on paper or is it?
I don't know, but Izar really likes analytical exams. So I think at least the first one will be analytical, and this is better for you because writing a code for cross correlation in 45 minutes or 100.5 minutes is also almost impossible. So, but calculating it after you understand the ideas behind it is very good. Oh, and here I can show you. So About cross correlation, I was talking about autocorrelation. Cross correlation is the same, but instead of the same neuron, you have it within two neurons. And then you shift them and you count the rate or the probability and so on. Okay, and I really want you to try and play with this. Benji built a very, very nice app. And this could be also useful for your project, that you put in the app itself a lot of definitions. For example, there are 3 neurons that are connected to each other. I think this is there are also instructions, and this is very intuitive. So you put 3 neurons and they are connected, and then you say this one is inhibitory, this one is excitatory, and so on. And then you just run simulate, and it draws the autocorrelation of each one and the cross correlation. Okay, so this could be really useful.
Here, asymmetric is not an article, it's not symmetric, right?
Right.
Yeah, okay.
Right, is asymmetric, yes. Yes. Okay, and I think this is the only thing that I wanted to say about cross correlation, that instead of the same neuron, this is another neuron. So let's try to do this one. Okay, only the second subsection. And then I don't know if we'll make it to the RO curve and PSTH, but it's okay. We have enough time during the recitation itself. And again, I said I feel this is much easier than all of these Poisson and probabilities and this kind of things that you have to do the math, but it's really hard to imagine, okay? Okay, so this question is, neuron A fires regularly at 10 spikes per second. T equals 0, 100, 200, 300, and so on, okay? And following each spike of A, neuron B fires 10 spikes at 1 millisecond interval with initial delay of 20 milliseconds, okay? So the first one is 20, 21, 29, and then 103, 121, and so on. So the first subsection is draw the spike train of A and B. Okay, so this will be neuron A, and this will be neuron B. And this one fires at 0, 100, 200, 300, and so on, okay? And this one fires 10 spikes at 20 to 29. And here, 129 to 120 to 129. Okay? And again here, 220 to 229 and 320 and 329. Okay? Just 20 millisecond delay. Okay? Draw the cross correlation of A to B normalized to probability. Okay? So now the question is different. Let's say that I am in the bus station, and I know that one of my friends, one of my best friends, Aylan, will come within 5 minutes. What is the probability that my bus will come before or after? Okay, for example, that my bus will come 20 minutes after Aylan. Do you understand the difference? This time I'm not waiting only for the bus, for the spikes to come. Now I'm looking at 2 sources of events. One of them is Aylan coming, and the other one is the bus. Okay, and each one of them is a spike. So let's first look at the spike over here at 0. Okay, so in our cross correlation, what is the first time lag that there could be? 20. Right. And in what probability? 1. Yes. And the next one? 21. And this is also 1, and so on until 29, right? Good. And now, what is the next one? 100, 120, right? Because I'm looking from this one to this one, not at the same neuron. So 120, full probability, and so on until 129, full probability. Okay, so therefore the positive part of the cross correlation will be all at 1, and here this is at 20 to 29, and here this is at 120 to 129, and so on. Okay? Do you understand the positive part? I'm looking from this one to this one. I'm just counting all the time lags possible. Yeah.
It's timeline and probably
Yeah, I'm sorry that the one is not that clear. It should be like this. Yeah. And now for the negative part, instead of looking at this one, I will look at this one. At the second one in the in A. This is the cross correlation from A to B. So before the 100, what was the time of the prior spike? I mean, like in B. How long did they wait from a spike from in B to arrive to 100? 71, yes. And another one at 72, and so on until 80. So therefore, here it will be minus 71, minus 72, and so on until minus 80, okay? And minus 171, minus 172, and so on. And this is again in probability of 1. Okay, now let's do the cross correlation from B to A. Yes. Yes.
For the first one, the most distant, the 120, for example,
Mm-hmm.
see like a log of 71.
Excuse me, I didn't fully follow.
Okay, so in 29 and 100, there is a lot.
Yes.
Then you put what's the 25.
Yes, exactly. Yes.
I think it's or like, I guess we start.
No, we started at this one, and then we look at what was preceding. This is what it means, the negative. That B was preceding A, right? Yes. So the idea, another way to solve it is just to take this and shift it, right? So how much do I need to shift it to get here? If I shift it left, 20. So when I shift left, this is the positive part. When I shift right, this is the negative part, okay? So now let's try to do the same, but now we will do the cross correlation from B to A. How do we do that? So we look at the spike here, the first one here, and what is the first time lag that it could have? 80. And is that the same thing for all possible spikes here? each one of them, if it weighs 80, would emit a spike. In how many cases? Only just the first one. So 1 out of 10. So 80 will be 0.1. And the next one is here. Here it's 79, right? This one weighs less, right? And also this one. So that the first one is 71 in this case. So it's true that I started from this one, but as I moved forward, I had smaller time lags. So in this cross correlation, I will start from 71 to 80, and then again 171 to 180, and all of them will be at probability of 0.1, right? Now let's look at the negative probability. What is the negative probability? Let's look at this bunch of spikes here. 20 minus 20 will be the first one, and then we will have all of these spikes here, right? Again at 0.1. Okay, and it goes on and on. Okay, so this is a nice toy problem. And please look at the recitation notes I showed. Oh, now I see that in the video they see nothing from the board. But you have everything in the recitation notes. So please look at also at the example of a regular Poisson exciting a regular neuron exciting a Poisson neuron. And then it changes its rate function. Okay? Yes. Yes. In a way, yes. Exactly. Yes.
For the question of whether A excites B, it's kind of obvious from like the spike change from like first that like A excites B.
But maybe B excites A, right?
Yeah.
Because he's waiting for 10 spikes to fire a spike.
Just
So it's a nice question, but you can say that since this is a higher probability, so therefore there is a higher probability that this one excites this one. It's really cute, yes. Okay, and this is the one with the Poisson process, and I have given you another, this one is the one that I want you to try. Yeah, so this is, these two exercises are also, again, very good to study with from the exam, and I also have simulations and solutions to them if you need, okay? So, so it's this one and the one next, it's slides number, I'll tell you in a minute.
We have all the solutions.
You have, sorry?
The solutions is one.
I'm not sure I wrote them in the presentation, but I can send you. So this is slides 12 and 13. So it's this one that they're alternating the ISIs between 100 and 200, and also the next one. No, this is okay. This is it's okay to look at it, but it's more like a full understanding that if it inhibits, there is a trough, and if it excites, so there is a peak. But it's not really. This one, I think, is really good. Okay. So 12, and I think that's it for today.
I just don't remember why the second time that the correlation, the probability was 0.1 instead of 1.
Yeah, because not for each spike here, you will have a spike within 80 milliseconds. It's only for 1 out of 10 truth, right? So the probability is 0.1. Okay. So if you wish to get ready for tomorrow, you can still look at these 4 slides over here, if you feel like, but you don't have to. And we will speak. I will also add them to the recitation notes this week. Great. Okay, see you.
נפגשנו אז שזה, אז בטח שאלה לגבי הנפקדות, ולא נראה לי שהבנת את השאלה שלי.
יכול להיות.
כאילו ציירתי אותה.
אז בוא תצייר לי אותה.